Hello, everyone. Welcome to our very first fall seminar. So hope you are all having a great start to the semester. And we're pleased to have with us today as our speaker, Professor Nick Whiteley from far away in England. Nick is the Hale-Bond Chair in Data Science at the School of Mathematics at University of Bristol, and he's also a Turing Fellow at the Alan Turing Institute. He received his PhD from the University of Cambridge in statistical signal processing, and later on he was also a Brunel Research Fellow at the University of Bristol. He has varied research interests across statistical theory and methods, including inference from high-dimensional dynamic stochastic systems, nonlinear filtering theory and algorithms, interface of convex optimization and probabilistic modeling, and also geometric aspects of high-dimensional data analysis. And of course, he has lots of high-quality publications in all these areas. And today he's going to tell us a little bit about some of his recent interesting work regarding discovering latent topology and geometric structures from high-dimensional data. So please join me in welcoming Nick virtually. And Nick, whenever you're ready, please go ahead.
Great, thanks very much. Let me just do the share. Hopefully this works. And I go to full screen. Okay, does that look okay from your end? Good. Well, thank you very much for the kind introduction, and of course for the invitation. This came about because I was in touch with your colleague Patricia a few months ago, actually, because we have common interests in an overlap in our work too with epidemic models, and it was on the basis of that this invitation sort of came about. But I'm actually not going to talk about my work on epidemic models today. I'm going to talk about some even more recent work, which we just posted on something on Archive 2 days ago. So it's very hot off the press. I think this is the first time I've really talked about it. It's work with Annie Gray, who's a PhD student here in Bristol, and my colleague also in Bristol, Patrick Rubin Delanchi. He's also based here in the School of Maths. The thing we put on Archive is a sort of journal length paper, and there was a short kind of partial version of the work, which was at a conference last year. Some of you may have come across this general notion called the manifold hypothesis, and it's not really a hypothesis in a really precise mathematical sense. It's more just a kind of general cover, a general collection of ideas that is sort of supported in two ways. So it's often found to be true in all kinds of high-dimensional data, and in some situations it can be explained sort of intuitively, although often somewhat heuristically, in terms of physical or mechanistic properties of whatever the data generating mechanism is. And I'll show you some examples of that in a moment. And it's also supported in a way because there's quite an array of statistical techniques, data analysis techniques, methodology, and also statistical theory, which is sort of predicated on this idea. And again, I'll come to some examples of those in a moment. Now, I imagine that some of you will automatically be thinking, okay, well, what do we exactly mean by a manifold in this context? What do we mean by embedded? Well, all those details will become a bit clearer as we go along, but I thought to start with, I'll just show you a couple of examples which convey this idea. The first one is a fairly well-known kind of phenomenon that comes up in the context of image data. Okay, so what are the data in this situation? They're a collection of photographs of one object, but just taken from different angles around a circle in the horizontal plane. Here there are 24 photos. The full data set is 72 of them. And each photograph is grayscale. It's a digital image with this many pixels, so that I can think of each image as, if I wanted to, as a vector in this dimensional space. And if one applies PCA to these data to reduce their dimension, while having a look at the variance explained by the principal components, you can see that those eigenvalues drop off fairly rapidly. And if I project data down to the first three principal components, what I see is something like this. Okay, so I've labeled these points according to the camera angle from which they were taken. Of course, PCA doesn't know anything about that, right? I've just given PCA the images, and of course, PCA doesn't know anything about the order of these images as well, right? You just present them a collection of data, and in some ways, it's quite striking that the pattern that emerges is a sort of something like a ring, right? But somehow distorted or twisted. And a ring which apparently seems to resemble the circle of positions from which the pictures were taken. Okay? And, you know, not thinking too precisely about it, maybe that's not intuitively outrageous, right? I mean, when we think about this collection of images, somehow the variability across this collection of images, we know it should be explained in terms of the position of the camera around the circle. Right? But that doesn't explain everything about what we're seeing here, right? Why do we see a ring which is somehow distorted and twisted in this particular manner? And moreover, you know, I've just shown you the first three dimensions from PCA. Well, you know, I've only done that for ease of visualization. What's in the other dimensions? You know, what might they convey about the situation? So these kind of questions are there. Just one example of these embedded structure. Here's another example. What's the data this time? Well, they're genotyping of DNA from people. Right? There's 3,000 people in total, and here the data are reduced down to 2 dimensions using PCA. This is from a paper from a few years ago from Nature, and the points obtained from PCA have been, you know, colored and marked with the country of origin of the person. Okay, and again, it's kind of quite striking that one is led to make an association between what we're seeing in the result of PCA and the geography of Europe, and that's kind of the big result of this paper. And again, somehow, you know, at an intuitive level, maybe, you know, it's not completely mysterious, right? You can sort of imagine that there may well be some relationship between the correlations between the DNA of different individuals and their locations, but that doesn't really tell us in any precise way why we see exactly this pattern. And again, you know, this is just looking at the first 2 principal components. Why should we look at those? So there are questions that remain. One more example. So this is a bit of a different flavor to it. This is a data set of documents. It's a subset of what's called the 20 newsgroups data, which is a kind of benchmark data set for things like topic modeling, and it comes along with scikit-learn in Python these days. And for each document, there are this many features which are to do with frequencies of words and so on in those features. And on the left, those data have been reduced down to just 2 dimensions by PCA. And on the right, data have been reduced first down to 20 dimensions using PCA, and then from 20 dimensions down to 2 dimensions using something called T-SNE or T-SNE. SNE stands for stochastic neighbor embedding. And if you're not familiar with what that is, it's a kind of nonlinear dimensionality reduction algorithm where you give it some collection of high dimensional data, and it tries to find a set of points in a lower dimensional space, which minimizes some measure of distortion of pairwise distances, right? So in sort of the pairwise distances between data in the lower dimensional representation are supposed to resemble the pairwise distances in the high dimensional input data. And what's the coloring here? The coloring is the news groups from which these documents were extracted in the first place. Okay, so PCA and T-SNE doesn't know anything about these categorizations. This is just how the points have been colored, and we see that, you know, collapsing right just down to 2 dimensions with PCA, if the colors weren't there, you wouldn't easily be able to pick out much of a kind of clustering structure. But if we do this combination of PCA first and then T-SNE, well, the clusters that we get, you see that they seem to tally quite well with these document labels, right? So somehow what I'm trying to convince you is that this example seems to have it has some things in common with the previous examples, right? So in the previous examples, the underlying structure was to do with kind of physical location, right? In the context of the photos of a car, it was physical location of a camera. In the genomic example, it was, you know, the physical locations of people. Here, the latent sort of structure is not a location like in a Euclidean space. It's something which has, as you can see, some hierarchical structure to it, but it doesn't have any inherent sort of geometry to it. But nevertheless, that structure is somehow related in the geometry of what we're seeing in the data. Okay, and what I will talk about is some work that we've done in trying to explain these kind of phenomenon of embedded structure in data, which seems to resemble something latent, as a general kind of statistical phenomenon. And, I explain what I mean by a statistical phenomenon as we go along. But at this stage, it's probably the right time to now be a bit more precise about when I say a manifold, what do I mean? So first of all, let's just talk about homeomorphisms and diffeomorphisms. For the purposes of this talk, when I talk about homeomorphisms, it will always be between 2 metric spaces. And spaces each associated with some notion of distance. And a homeomorphism between 2 such spaces is a map which is continuous, and it's invertible, and its inverse is continuous. All right. And then what's a diffeomorphism? Well, it's something which, in addition to being a homeomorphism, is something in which there's a notion of differentiability of the mapping in question and differentiability of its inverse. All right. Now, what notion of differentiability is used is sort of context dependent. So let me just show you a couple of pictures, and then I can explain the relevance of what's going on here. So on the left, this left pair, this teacup and a donut. This is almost stereotypical example of a pair of sets which are homeomorphic to each other. All right, and the way one can intuitively understand that is that a sufficient condition to be homeomorphic is that I can deform this set into that set by bending and stretching and twisting, but without tearing or puncturing or gluing things together. Okay, so that would, those kind of operations that I've just said verbally, if a function phi corresponds to those, then one has a homeomorphism, right? And so the idea is that the donut has just got one hole in it, and so is the teacup here, basically. Okay. But those deformations by bending and twisting, they're sufficient to define a homeomorphism, but they're not necessary. So, for example, this donut is also homeomorphic to this knot here, but I can't get to here from here to there without somehow tearing the donut, right, and then sort of twisting it and then somehow gluing it back together. Okay, so when I think about what it really means to be a homeomorphism, at least in terms of between sets which are subsets of Euclidean space, it's quite convenient to think about curves. Okay, so imagine that I take a curve which is somewhere on the surface of this donut. So what do I mean? I just mean, a line segment. Let's say it's not a straight line segment, but just a curve somewhere here. And then whatever the phi is that maps this donut over to this knot, I map that curve through phi. Okay, and if phi is a homeomorphism, the resulting thing still has to be a continuous curve. Okay, and vice versa, if I start with a continuous curve over here and I map it through the inverse of phi, the thing that I get must still be a continuous curve as well. And that's just because of the continuity of phi and its inverse. Okay. Now, as I said, difference between a homeomorphism and a diffeomorphism is that for a diffeomorphism, we also require that phi and its inverse are some sense differentiable. And so when I start to think about maps between arbitrary subsets of Euclidean space like these, the first obstacle I come across is that none of these is a linear subspace of R3. Okay, and because none of them are a linear subspace of R3, that means the usual notion of directional derivative of phi is not going to be well defined, right? I need to be working in a vector space basically for the usual notion of derivative to make sense, and these sets are not vector spaces. So one way that you can still kind of speak of differentiation of maps between such sets is in terms of differentials along curves. Okay, and suppose now that I come back to this idea of a curve here on the donut, and let's call that eta, and I ask about what that curve gets mapped to through phi. Well, if the resulting curve is which is this thing over here, is differentiable, and if I start from a differentiable curve over here, and when I map it back, I get a differentiable curve, then we can say that these two things are diffeomorphic. Okay, so it follows from that this teacup, assuming that it's actually got sort of non-differentiably sharp corners to it, is not diffeomorphic to this nice smooth donut. Okay, because I could get a differentiable curve over here, which is mapped. Sorry, maybe I should take one which goes sort of around the hole, and which gets mapped to something which is not a differentiable curve over there. And similarly, between these two pair of sets, I could have a differentiable curve on this knot, which gets mapped to something which goes around a sharp corner. Okay, so so in order to be diffeomorphic, we can't have one set which is smooth getting mapped to another set which is non-differentiably smooth. Okay. Now, I've talked so far primarily about the cases where the sets in questions are subsets of Euclidean space, but the notion of a homeomorphism is certainly not limited to that context. And here's another example of a homeomorphism. It's a much more mundane example, but one which will turn out to be relevant later. So let's think about the case where now U is just an abstract set with three elements, A, B, C. And let's think about the case where V is a collection of three vectors, say in R3. Doesn't have to be. Well, for two such sets, I can always consider U as a metric space if I associate it with this discrete metric. And I can always consider V as a metric space if I, just by using the Euclidean distance between those 3 points. And U and V, equipped with that distance metric and the Euclidean metric, are homeomorphic, right? What is the phi? Well, I can just associate VA uniquely with A, VB uniquely with B, and so on. Okay, and the continuity of phi and its inverse just are automatic when I have this kind of discrete structure. It's a kind of a notion of topological equivalence, which has a bit of a different feel in the discrete context than it does here, but nevertheless, these are just different facets of this general notion. Of course, when I come to this situation, well, there isn't really any sense in talking about a diffeomorphism using any sort of any standard really notion of differentiability of maps between the two, right? Because everything is very discrete. So homeomorphism kind of makes complete sense here. Diffeomorphism doesn't really make sense. Okay, so now that I've got those notions introduced, I can say what a topological manifold is and a differentiable manifold is. Well, in the context of metric spaces, M is a topological manifold if it's locally homeomorphic to Z. What do I mean by locally homeomorphic? Well, it turns out I won't really need to rely on that definition, so I'm not going to make that truly precise, but you can probably guess kind of what it might mean. And a differentiable manifold, well, is something which is locally diffeomorphic to some underlying set. Okay. And as we go on, the word manifold will crop up a few times. When I need to, I'll qualify what kind of manifold I'm talking about, but it'll be self-explanatory, I hope. Okay, so I mentioned that this idea of the manifold hypothesis is supported by statistical theory and methods which are predicated on this embedded manifold structure in data. And if I was to give a full account of all these methods, it would take an entire lecture course. But here are just a few examples. Well, there are some statistical techniques which have been designed to, for example, test hypothesis that a manifold is present, and that's in the context of Riemannian manifolds. I'll come on to the precise meaning of Riemannian manifold a bit later. There's also methods to estimate the intrinsic dimension of manifolds. Nonlinear dimension reduction techniques, well, I mentioned t-SNE earlier. There are others which do similar things. They try to sort of look for sort of embedded structure and flatten it out to find a lower dimensional representation of it. There are families of regression and classification techniques which are designed to exploit manifold structure in covariates. So if covariates are assumed to be concentrated on or near a manifold, then there may be clever ways to exploit that within these problems. And lastly, one can think of some clustering and TDA techniques as kind of predicated on embedded structure. Again, I'll come back to maybe if I have time to cut some examples of those later. And what's very common across all these kinds of methodology is that PCA is often used in practice as a pre-processing step, a kind of front end, where data come in very high dimensional, and often it's explained as just being something which is a computational convenience. They're often reduced down to, in inverted commas, moderate dimension using PCA before being fed into these things. Okay, as we go along, by virtue of the results that I present, we have a sort of some explanation for the validity of doing this. Okay, right. So far I haven't really said anything new at all. But what comes next is the new stuff. And what I'm going to tell you about is a statistical model called the latent metric space model. What is it? It's intended to be a simple and generic model. So I'm not trying to write down a very precise or accurate model for a particular data set or data from from a specific application domain. What I'm trying to do is to just introduce some generic and simple statistical assumptions, which can be thought of as representative across a wide variety of circumstances. And what I'll show you then next is that if one assumes that the data come from this latent metric space model, well, we can show that when we reduce the dimension using PCA, the PCA scores, I'll explain what they are in a moment, but it's basically the kind of things I was showing you earlier, turn out to be concentrated around a manifold. And why is that kind of remarkable? Well, the latent metric space model itself does not require us to explicitly construct any manifold. Right? What I'm going to show you is that this manifold structure just emerges from fairly elementary sort of statistical ideas, from ideas of correlation and latent variables and so on. And so the overall message of the work is that there's a we might observe seemingly kind of complex geometric and topological patterns in high dimensional data, but they could actually just be explained by quite simple statistical assumptions. And therefore, the ideas of the manifold hypothesis can be explained as a kind of general statistical phenomenon. And it will turn out that high dimensionality plays a key role in all of this, and that's why we've called this thing a law of large dimension. All right, how am I doing for time? Okay, so here's this latent metric space model. We've got a data matrix and with n rows and p columns, and it's constructed from 3 independent sources of randomness. So the first source of randomness is a collection of latent variables, which are assumed to be IID from some probability distribution mu, which is supported on some metric space Z. So Z is quite an abstract thing, just some sets associated with a notion of distance. The second ingredient is a collection of random fields. There are P of them, so that's equal to the dimensionality of the data, if you like. So what does it mean, a random field? Each X, say J, is a stochastic process whose domain is the metric space Z. Right, so what does that mean? It just means that if I fix a little Z in my big Z, then Xj of Z is a random variable. Right. And the third source of randomness is, inverted commas, noise. It's a matrix of random variables, which I'm going to assume all zero mean, and it's going to be convenient, although not really important. It's not really essential for the results that I'll talk about, that they all have unit variance. So that's the basic structure of it. So what you can see is that the idea is that the latent metric space Z, you can think of a set of sort of possible things, right? And each xj of Z is some random measurement associated with that particular member of big Z, okay? And we don't observe those measurements necessarily for every member of big Z. We observe the measurements associated with randomly chosen elements of Z. Okay, and then what we actually observe has some sort of, if you like, idiosyncratic noise disturbances on top of that. Okay, so it could be that let's say it turns out that big Z I here is equal to some big Z K. Well, the fields evaluated at those 2 points would be the same. But the observations might not be, because we've got some kind of idiosyncratic noise added on top. And we need to add a bit more mathematical structure to what this basic structure here to be able to prove things. And I'm going to assume that Z is compact. I'm going to assume that these random fields x1 to xp are mutually independent. And I'm also going to assume that for each j, the correlations across the z are continuous. Right? So the independence here is a mathematical convenience. Yeah, and if I get time later on, I can explain what would happen if you relax that. And for the noise, we're going to assume that the elements of this matrix E are uncorrelated across I, okay, and independent across J. So they're independent in the same sense that these X's are, okay. And that's it. That's the basic structure of this model. Now the PC scores, so these are basically the kind of quantities which I was plotting in the few pictures at the start. How do we compute them? This is basic stuff, but just to fix notation and to make sure we all have a common understanding of the terminology. I start with the data matrix Y. I take for some R the orthonormal eigenvectors associated with the R largest eigenvalues of this thing, which is, you can see, is up to a scaling is a covariance, sample covariance matrix. And to get these PCA scores, I just take the inner, I'm taking the inner products basically between the n rows of Y and these eigenvectors. Okay, so the interpretation of zeta is, it's just the coordinates of the ith row of Y with respect to the eigenvectors, the first R eigenvectors. Okay, so a simple picture. In this situation, the light dots are Y up to n, which are two-dimensional. In this situation, of course, the first principal component goes in this direction. The dark dots are what I get when I project the data onto that line, and the principal component scores are just how far along that line each of those points is. Okay. Good. So hopefully that's not news to anyone. But basically, these are the things that when you use PCA to do dimension reduction, basically this is what you calculate. Right. So one preliminary before I show you our first result, and it's this thing. I'm going to want to think about this quantity here. So it's a function of f and, sorry, it's a function of z and z prime, and it's just tells me something about the correlations averaged across the random fields which appeared in the model. And as you may know, Mercer's theorem tells us that there exists a feature map phi, which is a map from z to well, I can think of it as a map into infinite dimensional space, such that this kernel can be written in terms of inner products involving phi. Okay, so the perspective here is that the latent metric space model has been defined in terms of these random fields, and from those random fields I'm defining this kernel. Okay, and from that kernel I'm then deriving a feature map. Okay, now we come onto the main result. So what's it say? We make some assumptions about moments of the random fields and moments of the noise, and we also make an assumption that this kernel has a rank R. So that just means that if I look at the eigenvalues of the integral operator associated with that, well, it's the first R of them are non-zero and the rest of them are zero. That's quite a convenient mathematical assumption, which we put in place, not because we think it's really realistic, but because it's what we can accommodate in our proofs. And then suppose that from this data Y, we calculate the R-dimensional PCA score. So we're using PCA to do reduction in dimension down from P to R. Okay, and conveniently, it's the R which happens to match the rank of the underlying kernel. Okay, well, if that's the case, then what does this say? Well, if n is large enough, basically, and p over n is large enough, then with high probability, the principal component scores up to some orthogonal transformation and rescaling by the square root of p are uniformly concentrated around the evaluation of this feature map at the corresponding latent position, Zi. Okay. Where does this orthogonal matrix come from? If anyone's interested about that, we can perhaps talk about it later. But the thing is that because it's an orthogonal matrix, this tells us that the distance between zeta I and zeta j is concentrated around the distance between phi of zi and phi of zj. Okay. Right. Okay. So far, so good. But where's this manifold that I was talking about? Well, what I'm going to tell you about next is about the set in which these phi of zi's are valued. Okay, so that's what comes next. Okay, so remember we had some latent variables, z1 up to n, and they were samples basically that are valued in z. Okay, they were underlying the latent metric space model. We then calculated the principal component scores, and the principal component scores up to rescaling and orthogonal transformation were concentrated about the phi of the corresponding zi's. Okay, so those principal component scores are concentrated around this set. Okay, and as the notation would suggest, this set is going to be shown to be a manifold. Okay, so we need another assumption. This is an assumption on that kernel that I showed you back here. Where is it? This one. Okay, so it's this kernel which involves kind of averaging correlations across the fields. So what does this say? It's a kind of, you can think of it as a kind of distinguishability by correlations condition. So it says that for any z and z prime, I can always find some point psi, some third point psi, such that these two correlation kernels are different, right? And it turns out that if you assume that this is true, then this phi, this feature map, can be shown to be invertible, and moreover, m and z can be shown to be homeomorphic to each other. Okay, so you think back to those pictures before, the teacups and the donuts and what have you. Those were examples of homeomorphisms, and we find such a relationship here, right? We find that m is homeomorphic to z. And if we also make some more detailed assumptions to do the assumptions which are related to the smoothness of the kernel in general terms, okay, there's a bit more detail to it than that, but it's to do with the smoothness of the kernel, then not only are m and z homeomorphic, but they may also be diffeomorphic. Oh, and sorry, I should have explained. Under this A2, specifically, we're assuming that the latent metric space Z is itself actually a differentiable manifold. Okay. And we can say even more than that. It turns out that we can say something about the relationship between the geometry of M and the geometry of Z in this setting of A2. So what's going on here? Well, remember I talked about this notion of curves earlier and differentiation along curves. If I take some curve in Z and I think about the image of that curve in M, or the other way around, I start with a curve in M and I think about its image in Z, well, we've got a relationship here between, so this thing is the length of the curve in M, and this thing is something to do with the length of the curve eta in Z. Okay, but it's not just the length of a curve in the usual Euclidean sense, it's the length of a curve measured with respect to this kind of inner product where we've introduced a matrix H. Okay, and it turns out that this family of inner products, which appear here, are something called a Riemannian metric. Okay, and that's a way in which in Riemannian manifolds, geometry and specifically the notion of inner products and distances is a local notion. Okay, so what this says is that the length of a curve length of a curve gamma in M is equal to the length of the corresponding curve in Z, not with respect to Euclidean distance, but with respect to this Riemannian metric. And if one goes a step further and is prepared to assume a particular functional form for F, then we can calculate this matrix H, and we can say even more precise things about this relationship. So for example, these are just a few examples. If we assume that the kernel is some function of squared Euclidean distance that has this property, okay, so it has basically a local maximum G is 0, then it turns out that geodesic distance in the manifold M is proportional to geodesic distance in Z. Right? And for different families of kernels, for example, inner product kernels, translation invariant kernels, additive kernels, and so on, we can work through, calculate H, and find relationships between the geometry of M and the geometry of Z. But the overall message is that basically under quite mild assumptions, M is topologically equivalent to Z, i.e. homeomorphic to it, right? So it's sort of a topologically faithful Z. And under stronger assumptions, the set M is geometrically related to the underlying set Z. Okay. So here's an example. It's a case where the underlying set Z is a torus embedded in R3. Remember, in the latent metric space model, there were latent variables Z1 up to Zn, which were IID from some distribution mu, which is supported on Z. So let's just take that for simplicity to be the uniform distribution on this torus. And in this particular case, each xj is a zero mean Gaussian process with this Gaussian radial basis function kernel. And all that I've done here is that these points are 4,000 points sampled from the torus. It's the same 4,000 points here and the same as 4,000 points here, but all that I've done is that I've colored them differently. Here I've just colored them according to their angle with respect to this circle, and here I've colored the points in terms of their angle with respect to this circle. And as you may know, that a torus can be sort of a topological definition of a torus is that it's the Cartesian product of two circles. Okay, so these are, to say where a point is on this torus, I just kind of need to talk about coordinates with respect to these two circles. That's what I've done here. Okay, so these are our Zs. As I said, let's take the fields to be Gaussian processes with this particular kernel, and then have a look at the principal component scores. So remember, what the results said was that the principal component scores should be concentrated around a set which is topologically equivalent or homeomorphic to the underlying Z. Okay, and of course we can only really look at 3 dimensions of the principal component scores at a time. So it's difficult to get the full picture on our heads, but it's quite noticeable that somehow the first 3 principal component scores and also the next 3, they seem to tell us something about kind of coordinates with respect to this circle, right? And once we get to the next 3 principal components, oh, and by the way here, sorry, I should have explained, the points in the top row and the points in the bottom row are exactly the same. They're just colored differently, right? They're colored with respect to it's the same colors as the underlying points, the Zi's. So what we see is that the principal components 7 to 9 it's those which seem to tell us something about coordinates with respect to this circle here. Okay, and if you remember, I said that in this kind of situation where Z itself is a differentiable manifold, we can talk about the geometric relationships between M and Z. And because we've got this very simple form of a Gaussian radial basis function kernel, it turns out that the geodesic distance in M is equal to geodesic distance in Z up to a factor of the square root of 2, which that just comes from that matrix H that I showed you earlier. And if I numerically approximate the geodesic distances between points in this here and in here, and I plot them once again against once another, well, the red line is the theoretical square root of 2 relationship, and what we see is indeed that the geodesic distances that we get approximated via samples match that theoretical relationship rather well. And if we take things a step further, well, if we say, imagine if somebody had given us the data and we'd calculated these principal component scores, could we get back to the underlying latent variables, the Zs? Well, if we apply that T-distributed stochastic neighbor embedding, that's nonlinear dimension reduction technique I mentioned earlier, this is what we get, basically. And so it's kind of quite remarkable that we can somehow, in an entirely non-parametric way, get back from the data to the structure of the underlying set Z. You know, so I should explain that when you apply this T-SNE, there's no parametric assumptions to it, right? There are some tuning parameters to set, but there's no parametric assumptions involved. And yeah, so what we think is the case, that through this latent metric space model and our results, we can kind of go some way in explaining why things like this T-SNE technique might be useful. Okay. Here's one more example. I realize we're 15 minutes or so is up. So Abhishek, is it all right if I just have 2 more minutes, or okay?
Yeah, please go ahead. No worries. Yeah.
Okay. So you remember earlier when I was talking about homeomorphisms, and initially I talked about those, you know, the donut and the teacup and those subsets of Euclidean space. And I also mentioned a discrete example. All right. So what does the latent metric space model become if Z is discrete? It becomes a kind of finite mixture model, basically. So just for the sake of simplicity, let's assume that Z just has 3 elements to it, abstract elements, A, B, C. I can end out with that discrete metric I talked about earlier. And in that situation, you can see that the interpretation of the Z random variables, the ZIs, is that they kind of select which cluster the ith row of Y is drawn from. And the interpretation of the X's is that they're random centers for the mixture components. Okay. And so this is exactly the kind of situation we talked about earlier, where, so in this situation, what does a homeomorphism tell us? Well, it tells us that the image of Z through this feature map of the kernel should consist of 3 distinct points, right? Because Z consisted of 3 distinct points. And so if we go ahead and calculate our principal component scores in data that are drawn from a model of this form, they should be clustered around these 3 points. Okay. And indeed, that's kind of what you see. So here, this is just an example where the E's are a Gaussian. And what you see is that when n is fixed and p increases, in accordance with what the theory tells us, the data, once we calculate the PC scores from there, are increasingly tightly concentrated around 3 points. Okay. And well, what about the converse situation where p is fixed and n grows? Well, our theory doesn't really tell us anything very informative about what happens there. what you can see is that we still have got these 3 distinct points with clusters around them, but then the clusters are not getting increasingly tight when P grows and N grows. And looking at what that means in sort of a bit more at the level of the theory that comes from our results. So basically, if we plot this thing, as a function of N and P, okay, so what do we find? We find that when N is fixed, and as P grows, that error decreases, okay, which kind of what this is kind of what our theory tells us. On the other hand, when P is fixed and N grows, because there's some initial drop in that error, and then it kind of plateaus, or in some situations actually goes back up again, right? So our theory doesn't really tell us about the shape of these curves. What it does tell us is kind of what we see from looking this way, that once N is large and P over N is sufficiently large, then we should have this concentration. So a quick explanation of kind of why this is all kind of happening. And it comes from a dual interpretation of these principal component scores, right? So remember, they were calculated in terms of inner products with the eigenvectors of this matrix, which is a P by P matrix. The principal component scores can be rewritten in terms of the eigenvectors and eigenvalues of this N by N matrix, the kind of gram matrix that sometimes is called the data gram matrix. And that from that perspective, when we're calculating principal component scores, what we're actually doing is a kind of low rank approximation to this gram matrix. Okay, and moreover, under this later metric space model, the conditional expectation of this rescaled gram matrix has elements which are the inner products between these feature vectors, right? And sort of this is the connection, that when we calculate the principal component scores, we're approximately factorizing this matrix, and that matrix is a noisy version of the matrix which has the feature vectors maps in there. So one last slide is just signposting to a few more things that are in the paper. You know, this kind of flies a little bit in the face of what's sometimes called the kind of the idea of the curse of dimensionality. And so, you know, where's that curse of dimensionality? You know, why is it gone? Right? I seem to be telling you that having high dimensionality helps. Well, it's because of the dependent structure of this later metric space model, right? So instead of, you know, doing the usual thing of assuming that data are IID with dependence across dimensions for each data vector, we've done things differently, right? We've got data vectors which are dependent, although exchangeable, and for each data vector, we've got conditional independence across dimension. And there are some other connections to the literature. It turns out a special case of this model is something called the Gaussian process latent variable model, which was proposed as a way to do likelihood-based dimension reduction by Neil Lawrence. And there are MCMC and variational-based methods to do inference in this. So connections to the literature there. In the paper, we also have an investigation of what this means if we do classification or regression in the case where the PC scores are taken to be the covariates. We also have some work on how to choose the dimension of the PC scores, some new ideas there. And lastly, I'll just also mention that kind of related manifold structure, it turns out, shows up in spectral embeddings of graphs as well. So they're kind of, instead of doing an eigen decomposition of a covariance or correlation matrix, you do an eigen decomposition of a adjacency matrix or a graph Laplacian matrix under a particular statistical model. Similar kind of structure appears there, and my co-author Patrick has done some work on that. But anyway, I think I'm probably out of time, so I think I'll stop there.
All right. Thank you so much, Nick, for the wonderful talk. I'm going to open this up now to the audience and see if there are any questions. If you do, please just feel free to unmute yourself and ask Nick your question.
I have a question, if that's okay.
Yes, please go ahead.
Can you talk a little bit about dropping the assumption that the X1 to XP that were mutually independent? I think you had talked
Yeah,
about
sure.
that.
Sorry, I forgot to do that. I said I was going to do
Okay.
it. So let's go back to here. So if I go back up. Yeah. Okay. So what happens is basically when I come to think about this matrix, which is the n by n matrix, right? Under that independence assumption, and also under the independence assumption on the columns of the noise matrix E, this matrix product can be written as a sum of P independent rank 1 matrices. Okay, and it's that independence, basically this matrix is an average of P independent things, and we exploit that independence when we prove our concentration. Okay, so if you had an appropriate matrix concentration result, which could apply to the case where you didn't have P independent matrices here, but you had dependence, some weak dependence, then you can still hope for, I think it's fair to say qualitatively, the same phenomenon to be there. It's just the, you'll get hurt in terms of the constants or maybe the convergence rate and so on.
Perfect. Thank you so much. Yeah, that answered it very clear.
Yeah.
Is there any other question?
Can I ask whether you have an idea why the error increases if n increases for the fixed P?
Yeah, that's an interesting question. So, so I think it's to do with the nature of the error that we're talking about. So let me go back. It's the max, right? So say one way you can think about it, I mean, forget that this is like an error measure. Just imagine that, I've got n IID samples from, a Gaussian, right? And I ask for the biggest magnitude across n of them. Okay, so as n grows, that maximum is going to stochastically kind of grow, if you see what I mean. And so I suspect that's something, very loosely related to what's going on here. It's to do with the fact that we're talking about the maximum over n things, which in this context, they're not n independent things, but I suspect that we don't prove this, but I suspect that they're kind of weakly dependent.
So yeah,
Thank you.
like a follow-up on this question, and it seems like the error is increasing at a log n rate and you are taking maximum of n items. Yeah, and so I think the error should be of the order of log n, and your graph kind of agrees with that fact. So
right. Okay. Yeah. So you mean if they were independent, if they were IID, then we should have log n. Is that the?
Yeah. But I think even if they are weakly dependent, probably you should still have that log n rate.
Right. Okay. Yeah.
Even
Maybe
from
that's
the
it.
union
Yeah.
bound. Yeah.
I mean,
Yeah,
at least
maybe-
the graph seems to show like
Yeah, log
slowly
n rate.
increasing trend. Yeah, like
Yeah.
some kind of a slowly increasing trend.
Yeah,
Probably
yeah.
something logarithmic. Yeah.
Yeah. Exactly. Yeah.
I had a quick question. Actually, I've been meaning to ask this, like regarding your main theory result. I mean, it's fascinating. Later on, what you are showing that the results seem to do better when n is fixed and p seems to grow, as opposed to p fixed and n grow. So I was just wondering that bound in that main result on slide 12. Do you have a sense of what would be the rate of convergence and like the dependence of it on p, n, and r, the critical guys?
You mean beyond? You mean what's the best spot? The best rate that we could hope for. Do you mean, or?
So it seems to me like square root p over n and square like r to the 1/4 over square root of n. Those kind of guys are going to show up, right? So if I didn't sort of explicitly state this in terms of the epsilon or something, I just wanted to get a the sense of the asymptotic rate.
Yeah.
So I'm just trying to understand what rate must show up there for your numerical findings later on to sort of match up that if n is fixed and p increases, things get better. So it seems like p must show up somewhere in the denominator, right? Of the rate, which is counterintuitive.
Yeah, I mean, I guess it comes back to this thing about the dependent structure of the model,
Yeah.
right? And it's key that we've got this independence across dimensions. So it's, you know, whilst the random fields don't have to be identically distributed, you know, there's the independence there, and so there's some behind the scenes, there's sort of some averaging which is going on there across, but averaging across the dimension somehow.
I see.
Yeah.
Okay, but so is it, do you still know, like, can roughly say like what the rate would look like? Like, you know, like in usual estimation procedures, you would say, okay, this rate for a typical, you know, like high dimensional problem without any penalties or sparsities and stuff like that would be square root p over n kind of a thing, right? But that's not going to show up here, it seems to me, right?
So yeah, so what can I say about that? Yeah, so the short answer is that I don't have a very clear answer for you, but I can make one
It's
more
okay,
remark,
no?
so the element wise, the conditional expectation of this matrix given the latent variable z1 up to zn is the matrix with these elements. Okay, and when you ask for bounds on like the spectral norm between this matrix and the matrix with these elements, indeed there you get the p over n.
Right.
Yeah. But that's not the only contribution to the error. So the short answer is I don't have
It's all right, don't worry. No worries.
But it's a very important point. So you're thinking like, what if? So let me just, because
to validate or to sort of match up what you're trying to say in the later on in your like
yeah,
numerical
yeah,
n is fixed and p increases, things get better. So the error must decrease with, like, somehow the p must show up somewhere in the denominator of the rate, you know, like, as opposed to, so usually in high dimensional problems, you pay price for the dimension, so it shows up in the numerator somewhere of the rate.
Yeah.
Something like that. But anyway, never mind. Yeah, it's not the easiest question, I'm guessing.
No, I'm yeah, so it's the source of it, I know in the theory, will be from when you compare the conditional, you know, this to its conditional expectation, and there it's the in that bound in the proof you get n over p basically. Yeah,
right.
But it's a very good point. It would help explain precisely what we're seeing in those pictures if I could tell you about it. So thanks, that's really useful feedback.
No worries. Are there any other questions for Nick at this point? Well, if not, please join me again in like thanking Nick for the wonderful talk.